Our society has grown heavily dependent on our network of roads and highways. When transportation systems are functioning well, we take them for granted. But when there's trouble on the highway, we experience delays, traffic congestion, and inconvenience. Bridge rails might seem to be a small detail in comparison to the large, impressive structures where they're located, but they serve a very important purpose, keeping vehicles and the people in them on the roadway. This videotape will describe several concrete bridge railings that can be used to make bridges safer. Many bridge railings may not be adequate in an actual collision. The only sure way to determine the collision performance of a bridge rail is through full-scale crash testing. In 1989, the American Association of State Highway and Transportation Officials, AASHTO, adopted new guidelines for evaluating the performance of bridge railings. These new guidelines require that all new bridge railings be evaluated in full-scale crash tests. Requiring full-scale crash tests for all new bridge railing designs was not the only change in the AASHTO guide specifications. Because bridges in different areas carry different kinds and volumes of traffic, the AASHTO guidelines contain 3 performance levels to suit conditions at different bridges. Light passenger car and light truck traffic is common on many rural bridges. Requiring a high-performance bridge railing on a low-volume, low-speed bridge is not generally cost-effective since both the probability and likely severity of an accident is low. Some rural bridges fall into the first performance level category, PL1. A typical bridge in an urban area or on a highway carries larger volumes of traffic at higher speeds. Some of these bridges also experience more truck traffic. Because there is a greater probability of a collision and the collision is likely to be severe, these bridges require a more costly, higher performance railing. Most urban and highway bridges fall into this second performance level category, PL2. The third performance level, PL3, is for bridges where the combination of speed, traffic volume, and percentage of trucks make the probability of a serious collision relatively high. The consequences of a large tractor-trailer truck, bus, or tanker truck penetrating through a bridge railing can be very severe. The collision not only places the truck driver at grave risk, but other drivers on the bridge can be unwittingly drawn into the accident. If the truck penetrates the railing, the danger may spread to occupants of vehicles on other roadways as well as pedestrians. Recent crash test programs have evaluated a variety of bridge railings to determine their performance level. This videotape will review some of the results of these testing programs, starting with the PL2 bridge railing. The 1989 AASHTO guide specifications require tests with 3 types of vehicles: an 1,800-pound passenger car striking the barrier at 60 miles per hour at a 20-degree angle, a 5,400-pound pickup truck striking the rail at 60 miles per hour and 20 degrees, and an 18,000-pound single-unit truck striking the bridge rail at 50 miles per hour and 15 degrees. The bridge railings in these tests must prevent the vehicle or its cargo from penetrating or going through the railing, prevent vehicle or barrier debris from entering the passenger compartment of the vehicle, smoothly redirect the vehicle away from the bridge rail without causing it to roll over, and ensure that the occupant's impact velocity with the vehicle interior is below the specified values. Recently, several concrete bridge railings have been tested to determine if they meet the AASHTO PL2 criteria: the New Jersey safety shape, the F-shape barrier, and the vertical concrete wall bridge railing. The concrete safety shape barrier, also known as the New Jersey barrier, is without a doubt the most popular bridge rail in use today. One reason for the popularity of the concrete safety shape is that it effectively prevents vehicles from penetrating the rail while being nearly maintenance-free. The shaped profile of this bridge rail causes a vehicle to ride up the barrier as it is redirected. This vertical motion dissipates energy, resulting in less vehicle damage and better occupant response than the comparable impact with the vertical wall. This test showed that the occupant responses were within the allowable range. Since shaped barriers dissipate some energy by lifting the vehicle off the ground, there's a chance that vehicles may sometimes roll over, as happened in this test of the GM shape. This type of accident is almost always very severe. The small car crash test is designed to uncover this type of vehicle stability and occupant response problem. The 5,400-pound pickup truck test demonstrates the strength of the bridge rail for a larger vehicle. The barrier successfully redirected the pickup truck, causing only minor cosmetic damage to the bridge rail. The 18,000-pound single-body truck test is the most demanding test of barrier strength in the PL2 test series. In this test, the front of the vehicle rode up the sloped face of the barrier, then rolled 44 degrees until the cargo deck came in contact with the top of the vertical wall. Although the vehicle rolled over onto its side after leaving the rail, the vehicle was successfully contained, so the test was considered a success. Although the New Jersey shape is the most common shaped concrete barrier, it is not the only one. A research project in the mid-70s identified a number of alternative shapes. Alternative F, now commonly called the F shape, was identified as a promising candidate. The slope breakpoint of the F shape is 3 inches lower than the New Jersey shape. This slightly different profile provides many of the same benefits as the New Jersey shape while improving vehicle stability during impact. Like the New Jersey shape, the F-shaped barrier dissipates energy by lifting the vehicle up off the ground and by crushing sheet metal. The occupant responses in this small car test were somewhat larger than in the tests of the New Jersey shape, although they were still below allowable limits. The vehicle trajectory, however, was much better, minimizing the possibility of a second collision or a rollover. In the 18,000-pound truck test, the front of the vehicle rode up the face of the barrier and rolled 31 degrees until the cargo deck struck the top of the barrier. The F-shaped barrier performed better than the New Jersey shape in this truck test, since the vehicle did not roll as much and was redirected without rolling over. Perhaps the most basic bridge rail is a vertical reinforced concrete wall. This simple design is surprisingly effective in containing and redirecting vehicles in a crash without rolling them over. As the shape of the barrier becomes more vertical, the occupant responses become higher than for similar tests with shaped barriers. In the small car test, the lateral occupant impact velocity was essentially at the allowable limit. Although the occupant responses were only barely adequate, the vehicle was much more stable than with either shaped concrete barrier. Unfortunately, the wheels are frequently damaged, and this can cause the post-impact trajectory to be unpredictable. Unlike the safety shapes, a collision with a vertical wall almost always causes damage to the vehicle. Since the vertical wall has no sloped face, the energy of the crash must be dissipated through damaging the vehicle. Although the vehicle and its occupants experience greater forces during the impact, the chance of rolling the vehicle over is significantly reduced. In the single-unit truck test, the vehicle only rolled 18 degrees, much less than either the New Jersey or F-shaped barrier tests. The vehicle was more stable in this test than in previous heavy vehicle tests. Performance Level 3 bridge railings may be warranted for use on bridges with high truck traffic and adverse geometrics. By increasing the height of the concrete barriers from 32 to 42 inches and using different reinforcement details, these bridge rails can be used when a higher performance system is required. A PL3 bridge railing must perform well in crash tests with an 1,800-pound passenger car and a 5,400-pound pickup truck, as well as a 50,000-pound tractor-trailer rig. In a collision with a typical passenger car, the peak force of the collision may be as much as 60,000 pounds, acting at a height of about 20 inches above the ground. Since most bridge railings are between 27 and 32 inches high, the rail can provide the required force at the correct height for passenger cars. But as the vehicle becomes larger and taller, the height and magnitude of the impact force also becomes higher. If a bridge rail is too low, the truck will simply roll over on top of the barrier. When there's a good possibility that heavy trucks will strike a bridge rail, crash test experience has shown that the bridge rail should be at least 42 inches tall to provide an adequate force at the right height. The F-shape, New Jersey shape, and vertical wall can be used as PL3 bridge rails if their heights are increased to 42 inches and additional reinforcement is used. Damage to both test installations consisted primarily of scuff marks, scraping, and gouging of the concrete. The bridge railings would still be effective after these very severe collisions. Each of these barriers has its own advantages and disadvantages. The barrier with the least vertical face, the New Jersey barrier, causes the least amount of sheet metal damage and has the best occupant response. The vehicle stability for the shaped barriers is not as good as for the vertical wall. The vertical wall has the best roll stability characteristics, but it causes the most wheel damage, which can result in the vehicle re-entering the roadway. Improved vehicle stability is even more important in impacts with trucks. Although the shaped barriers contained heavy trucks, the vertical barrier keeps the trucks upright and more stable. Crash tests indicate that the F-shape may be a good compromise between the less favorable stability characteristics of the New Jersey shape and the higher occupant response characteristics of the vertical wall. There are trade-offs that must be made when deciding between the stability, post-collision trajectory, and occupant response characteristics of these bridge railings. These bridge railings satisfy the AASHTO guide specifications for PL2 and PL3 conditions. More important than simply meeting the specifications is the fact that the performance of these railings has been demonstrated in full-scale crash tests. Crash tests are the best available method for deciding which bridge railings designs will work and which designs will not work. Bridge railings serve an important, though usually unnoticed, role in providing a safer roadside environment. Choosing the most appropriate bridge rail may seem minor in comparison to other engineering and design considerations, but making the correct decision can save someone's life.